So what I want to talk about is lines and planes described in 3D, okay? And it's a little different than the form that you saw in 2D in algebra. But what I need to do is to go back to algebra to review a little bit of where you got that so I can explain the theory of lines and planes in 3 dimensions. So let's do that. Now, if you want to skip this theory and go straight to the example problems, you can. But I got to tell you, the more you know about this theory, the better you're going to be off in doing the problems, because the problems are going to ask you particular things that if you don't know the theory of how these equations are obtained, or you don't know what the quantities in the equations are, then you're not going to be happy, okay? So let's go back to some algebra, okay? So let's recall some stuff. It's very simple stuff. I think you remember it. So if it says if line L contains the points, let's say x1, y1, let's call that P, and the points x2, y2, let's call that Q, then the slope is m equals y2 minus y1 over x2 minus x1, okay? Now, so what you got here, what you got going on here is a line L, and you have a point P, and you have a point Q, and their slope between them is this formula here. Now, I'm not going to go into where the formula comes from. We don't need that right now. All right, now, what if Q is a particular point, this Q is a particular point on the line, this P is a particular point on the line. If Q is a random point on the line, okay, so if Q is a random point on the line, any point on the line, the formula is still the same. We label it, but we label it differently. So we label it x, y, okay, so not x2, y2, or with subscripts, okay, it's just x, y, okay. So what's the slope formula? The slope formula is still the same. It's going to be now y minus y1 over x minus x1. Before this was y2 and this was x2. We're talking about a random point on the line. Now, our goal is to find the equation of a line, okay? Find an equation of the line, all right, through P, okay, through P, with slope m given above, all right, with slope m. Now, this here will describe it. We're almost done. In fact, this is a good this is just as good of an equation as any other. Because why? Well, a line has the characteristic, the only characteristic of a line is that it has a certain slope and it goes through a series of points. That's all it is. Okay? So if you have a point P and it shares a slope with Q, the slope is the same between P and Q1 as P and Q2 and P and Q3. If those all share, all those pairs of points share the same slope, then there's only one line that satisfies that in 2 dimensions, okay? There's only one line that satisfies the fact that P and every other point on it have the same slope. So if I can get a formula that relates all these together, I'm done. I've found the equation I'm looking for. Well, here it is. It's right here, staring at you. But what they normally do is they cross multiply, and this formula is normally what you see. So what I'm going to do is I'm going to cross multiply. Xy is x1. So I'm going to write m over 1 now, and so this becomes y minus y1 equals m times x minus x1. And this is what's called the point slope form of a line. You don't need to know this, the name, just know how to use this, right? I mean, you see this all the time. All right, so this is the equation of a line. And so whenever you have 2 points on a line or a point in the slope, this is the equation you use. Now, what does this have to do with what we need today, which is lines in 3 dimensions, okay? So what I'm going to do is I'm going to redraw this, okay, over here where I can use it, okay? So now for 3D, now for the 3D version. 3D version. And we're going to use the same idea of slope here. All right. So I'm going to draw the X, Y, Z axes. Y, X, and Z. And here's my line right here. And I'm going to pick a random point on the line. Let's call it P. And another, no, not a random point. This is a particular point. We're going to call it X naught, Y naught, and Z naught. Okay. And then a particular point on the line, that's P. And then a random point on the line, we're going to call that Q. And that's going to be X, Y, and Z. Okay. So this Q could have been here. It could have been here. Could have been here. Could have been here. It could have been anywhere. Okay. So we could have drawn that anywhere, but I just drew it there for convenience. All right, so with that said, if you notice there's a slope between those, and I'm going to draw a vector that is parallel to the line, vector V. So V is parallel to the line L. So let's call this line L. All right. Now, if you notice, there's a vector that connects P and Q. All right. I'm going to call that vector. Well, let's not give it a name just yet. Let's just draw it. Now, there is a vector that goes up to P, and there is a vector that goes up to Q. All right, the endpoint of that vector that goes up to P, the endpoint is P. So I'm going to call this vector here, I'm going to call that R naught, because it corresponds to X naught, Y naught, Z naught. And I'm going to call this other vector, I'm going to call that R. Okay, and that corresponds to X, Y, and Z. All right. Now, in your theory of vectors, the vector that connects these two, this vector right here, is R minus R naught. Okay, that is R minus R naught. Now, R minus R naught is, so here, let's say note, R minus R naught is parallel to V, and it has a certain length to it, okay? It's parallel to V, it has a certain length, so depending on how long it is, it's either longer or shorter than V. Fine, okay? So since it's longer or shorter than V, they're off by a constant. So this one here and this one here, they're off by a constant. So let's say thus there is a constant t. Should I say constant? Let's say a t, and I'll determine if I want to use constant or variable in just a minute. There is a t such that R minus R naught is equal to t times V. Okay, so basically this is if, all right, so if t is a half, then R minus R naught is shorter than V. Okay, shorter than V. Okay, all right, now we have this formula. What this formula gives us is it gives us this R minus R naught, which I'll draw here. This is R minus R naught. All right, now if you don't understand why that's true, go back into the vector theory, all right? We have this R minus R naught, and that is equal to a version of V. It's a version of V here. It's either a longer V or a shorter V, and that describes this equation here. This describes the line completely, because if you pick any random point Q, R minus R naught, the point R, which is represented by Q, those will also be parallel to V. Okay, so let me write that down. So since R is a vector representing any random point on the line, all right, then r minus r naught will be parallel to v regardless of where r ends up. It's always going to end up on the line, but it could be anywhere on that line, okay? We said that before. It could be anywhere on the line, okay? So this is the equation we need, and sometimes we write the r naught on either side, so it's r equals r naught, let me draw a little smaller, r naught plus tv, all right? Now, t is kind of a variable, but it's also a scalar in a sense. It's going to be a variable, but it acts as a scalar as soon as you plug a number into it, okay? So let's do an example of this, okay? Let's see what we got up here. Let's see what we got. I'm going to get to these here in a second, okay? I don't want to get to that just yet. Oh, okay, so this is the formula that we just derived. Find a vector. Okay, so it's all this stuff. Let me just do an actual example that I'm just making up. All right. So an example of this would be find a vector equation of the line through the points. Let's say 1, 2, -3, and -1, 4, and 6. Okay. So you have some random line in space. You have some line in space. I don't know where these points are. Okay. Actually, let me not draw the axes. Let me just draw the line. Okay. So you have a vector that ends up at 1, 2, -3. Well, I'll tell you what. Let me go ahead and draw that. Somewhere in space, there's a line, and then you have a vector that ends up at the other point, and that other point is -1, 4, and 6. Okay, so what we want to do is we want to find the equation of this line, so 1, 4, and 6. Okay, so what you do is you need to find this vector r minus r naught here. Okay, you need to find this vector. Okay, you need to find a vector parallel to it. So that vector is somewhere down here. We'll call that v. So v will be the difference of these two. So it'll be -1 minus 1, 4 minus 2, and 6 minus 3. Okay. So then v is -2, 2, and 9. Like that. And then, so that's v. And now you can just plug in what you got. So we have r. Let me draw this in a different color. We have r equals r naught, and I suggest you write this down every time you need it. It's r naught plus tv. So then r naught is any of these 2 points. So I'll use the first one, 1, 2, -3, 1, 2, and -3, plus t times v is -2, 2, and 9. Let me check that. That was -1. Dang it, get away. -1 minus 1, -1 minus 1, and then 4 minus 2 is 2, and then 6 minus 1 is 3 is 9. Yeah, that's it. Okay, so now we just keep going with this. So r is 1 minus 2t, comma 2 plus 2t, comma -3 plus 9t. There we have it. And so that is the vector form of the line. Okay. So r, remember though, so that's our answer. R, remember though, was the point x, y, z. All right, where was it? Here it is. See how r ended up at x, y, z? So you can write r as x comma y comma z, like that, like we did. Okay, so that's what I'm going to do. So I'm going to derive. I'm going to show you there's another form of the line that you can use. So we have x y z equals this 1 negative 2, 1 minus 2, 2 plus 2t, and then negative 3 plus 9t. And then, so then x equals 1 minus 2t, y equals 2 plus 2t, and then z equals negative 3 plus 9t, like that. And so what this is are the parametric forms of the line. So parametric forms. This is the parametric form of the line. Okay, so we did this before in parametric equations, right? It's just that you didn't have this z here, you only had y and you had x, okay? So remember, you would write it with parentheses, with these brackets, you would say x equals 1 minus 2t, and then y equals 2 plus 2t. Well, it's the same thing here. You can write now z equals negative 3 plus 9t, and so that's a parametric form of the line. So let me get rid of this yellow. All right, so that's a parametric form. Now there's another form, just to make things more confusing for you, which is what math likes to do. There's another form. I mean, like the vector form for me is good enough. Okay, we're done. But the book's going to ask you for the symmetric form. So what I'm going to do is I'm going to take what I have and I'm going to solve for t in each little equation. So for the, let me just do this in a different color because it's a new one. What's a good one? How about this green? So for the symmetric form of the line, we're going to solve for t in each. Okay, so on the first one, it'll be, let's see, x minus 1 over negative 2 equals t. And then on the second one, it'll be y minus 2 over 2 equals t. And then on the third one, it'll be, oh, just negative 3 plus 9t. Wait, time out, what am I doing? This is z plus 3 over 9 equals t. Now, all these are equivalent, so what you can do, because they're all equal to t, so you can, what we can do is write x minus 1 over negative 2 equals y minus 2 over 2 equals z plus 3 over 9. And that is the symmetric form of the line, okay, symmetric form. I'll probably never ask you for that. I may ask you for the parametric form, but mostly I'll ask you for the vector form of the line. Or I might just say find the equation of the line, and you just pick your favorite one, okay? So as you can imagine, things get a little more complicated than that. So let's look at one of these problems up here, and let's see what a good one might be. All right, so yeah, so what they have up here is, this is out of the book, they have the parametric and symmetric forms of the equation. Oh, one thing I want to show you is the coefficients of t are a vector parallel to the line, okay? So that's one major fact, right? So when you draw this out, I mean, sorry, when you work this out, if you look, see how this vector v, this green vector v, was parallel to the line, and this vector v was negative 2, 2, 9. So when we did our work, negative 2, 2, 9 showed up as the coefficients of t, all right, t. And over here, negative 2, 2, and 9 showed up as coefficients of t, all right? So the coefficients of t will be a vector parallel to the line. And that's why I don't like symmetric so much, because that goes away. All right, so let me give you that little fact. Let's write that down. Fact, the coefficients of t yield a vector parallel to the line. Okay, to the line. So when we got to keep that in check here, not in check, but in mind. I suggest you memorize that or just know it. Okay. A lot of math isn't memorization, it's just knowing stuff. All right, so what looks good in here? Let's see what we can do. It says find the vector equation and parametric equations for the line. We did something like number 7 already. How about number 4? Let's do number 4. So what I'm going to do is I'm going to cut it out, and we're going to paste it over. All right. All right, so I pasted it over here, and let's see what we got. It says find the equation of the line through this point parallel to this line. All right, so if it's parallel to this line, then we know that v is going to be the coefficients of t. So it's 2, -3, and 9. Okay, and it looks like the point on that line, we don't need the point on the line, but the point on this line would be 1, 6, I'm sorry, -1, 6, and 3. Okay, we don't need that right now though. Okay, so we have a vector v, and we have a point on the line too, this point on this line. So the equation of the line is r equals r naught plus tv. R naught is any point on the line. Well, we got that. We're almost done with this problem. So it's r equals, all right, as a vector, 0, 14, -10, plus t times 2, -3, and 9. They're parallel, right? They're parallel. So you can use the same vector v that is parallel to the given line for our vector v that is parallel to the needed line. It's kind of like using the same slope in point slope form, like ln x plus b. All right, so this is r equals 0 plus 2t, 14 minus 3t, and -10 plus 9t. And we can just clean this up. R is 2t, 14 minus 3t, and then -10 plus 9t if you want. And then the parametric equation, this is the vector equations here. The vector equations, the parametric, sorry, would be x equals 2t, y equals 14 minus 3t, and then z equals -10 plus 9t. Okay, so now let's try another problem. All right, let's go back and look at the problem set and see what we got. So let's look at this. All right, so I'm going to look at number 20. Let's try number 20. All right, so let's pull it over. All right, so here we go. So line L1 has the vector v1, which is -12, 9, and -3. And vector v2, this is line L2, has a vector parallel to it, 8, -6, and 2. Now, they're just using, this S is a new parameter. All right, it's just a new or different parameter than T. We don't want to use T because, different. We don't want to use T because if you give a value of T for the first line, it may not correspond to where the second line is, okay? This is a new or different parameter. All right, so let's see here. Are these related at all? No, they're not. I think if I divide by 3, let's see, divide by, let's see here. If I do -12 equals 8x equals 8, let's say m, then m is -12 over 8, which is -3 over 2. Let's see. Ah, there we go. That's it. Yeah, they are related. And see, 9 is equal to -6m. M is equal to -3 over 2. And then on the other one, -3 equals 2m. M is equal to -3 over 2. M I'm just using as a variable. I don't use x because x is associated to the first coordinate. All right, so since they're related, then they're parallel. Right? They're related via product by a number. So if you note, if I multiply 8 times 3 divided by 2, that would be -12. So it looks like v1 is equal to -3/2 v2. And so since these two vectors, I'm sorry, I should have been writing vector notation. Since these two vectors are off by a constant, okay, one is a constant multiple of the other, this means that v1 is parallel to v2, and that implies that L1 is parallel to L2, and we're done. Now, look for the book for an example. The book has an example of a skew lines, right? All right, so now let's look at planes. So let's go on up there. Okay, so I'm going to make my way over to the blank part of the screen, so planes. So let me draw. So first of all, the formula for a plane is n dot r minus r naught equals 0, where n is perpendicular to the plane, it's orthogonal to the plane, and r naught are vectors whose endpoints are on the plane. Endpoints on the plane. Okay, so let's draw this scenario out. Okay, so the way that the book does it, I'll do it the way the book does it so you have it for reference. So they draw the x, y, and z axes, and then they have this nice plane running through it, like this, something like this. And I can do better than that. All right, so I said that r, let me do this in red, r, let's say this is, let me see, let's see what they do here. I think they make that r, yes they do. Okay, it doesn't matter. I want to be consistent with the way the book does it, because then if you have to refer to it on your own, then you've got it. All right, so this one is r. All right, so its endpoint ends at q. So let's say this is q, which is x, y, z. It's a random point on the plane. And then r naught is another vector which ends on the plane, and that one is p, which is x naught, y naught, z naught, and then so y naught comma z naught. So this is r naught. So r is the vector x, y, z, and r naught is the vector x naught, y naught, z naught. All right, so when you have a vector ending at a point x naught, y naught, z naught, you call it x naught, y naught, z naught with these brackets here, these brackets. Remember that from vector theory. Okay, so then we have this scenario. Now, r minus r naught, we had this before, was this vector like this. So in green, we have r minus r naught. Remember, you complete the triangle, and the vector points toward the first term, okay? Points toward the first term. That's how it's drawn. Okay, now r minus r naught is a line, it's a vector on the plane. Now, a vector on the plane, we could have drawn r anywhere on this plane, okay? So if I wanted to, I could have drawn the plane like this, and then my x, y, and z over here, and I could have drawn it so that r ended up here, and then r naught was still this vector here. Here's r naught, okay? So r can be anywhere. R is a random point. R is a random vector whose endpoint ends on the plane, okay? And then r minus r naught would have been this vector here, okay? That vector is on the plane just as much as this other green vector is on the plane. So basically a plane it's just composed of a bunch of lines. Let me draw them in green. It's just a bunch of lines that kind of end in vectors if you want, okay? They're vectors, okay? But just a bunch of vectors. So this is my plane, like that, all right? Okay, so if I find a vector that's perpendicular to all of these, let me call it n, perpendicular to all of these, then I know that when I take the dot product of these vectors, I'll get 0, okay? So if there is a vector that's perpendicular to every vector on the plane, then that vector's dot product with the plane vectors is 0. So if I look at any random vector in the plane and I dot it with this n, so let n be a vector perpendicular or orthogonal, if you want, to the plane. And let's give it a name. Let's say n is ABC. ABC. Okay, so then n dotted with r minus r naught, which is some random vector on the plane, this is equal to 0. This is since it's perpendicular. All right, well, that is our formula that we need. Okay, so n dotted with r minus r naught equals 0. This is the equation of a plane. Equation of the plane through r naught and perpendicular to perpendicular to n, like that. Okay, so if we let n be ABC, so ABC dotted with r is xyz minus r naught is x naught, y naught, z naught as a vector. Ooh, come back here. This is equal to 0. So now if I want to do this mathematics, so first of all, the interior here is x minus x naught, y minus y naught, and z minus z naught. Come back here. Z minus z naught equals 0, and this is dotted with ABC. And now if I do the dot product, this is a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And now if I multiply this through, I get ax plus by plus cz plus, and then it's negative ax naught minus by naught minus cz naught equals 0. Notice that the coefficients of x, y, and z are that n. Okay, n was ABC, and if you look at the equation of the plane, the coefficients of x, y, and z are ABC. This is n. So this means then that the coefficients of x, y, and z of x, y, and z yield a vector perpendicular or orthogonal to the plane. In other words, to the plane. This is your n. All right, so let's do an example. So what I'm going to do is I'm going to move up, grab an example, and then come back down. All right, so here we are. Let's see. Let's try 26 first. So we want to find the equation of the plane through this point and perpendicular to this line. Now, this line, remember the line has a vector v parallel to it. Okay, it doesn't have a vector v. It let's say the line is parallel to the vector v equals 3, -1, and 4. All right, I'm getting that from the coefficients of t. Coefficients of t give a vector that's parallel to the line. We went over that in the last stuff. So we have some plane in space, okay, and it is perpendicular to this line. So let me draw the line in blue. So here's a line. Good old line. And it is perpendicular to the plane. Well, if it's perpendicular to the plane and v is parallel to the line, so v is somewhere out here. Let me draw v in red. So v is somewhere out here, and v is this vector here, and it's parallel to the line. We can use v for n, because we need a vector perpendicular to the plane, v for the n, the required n. Okay, so let's do it. So we have our plane equation, n dotted with r minus r naught equals 0, and I would really recommend you write this out every time so you've memorized it. Okay, so let's see what n and r naught are. N is 3, negative 1, 4. So we have 3, negative 1, and 4. R is that x, y, z. So that would be x, comma, y, comma, z. And then minus r naught. Well, what's the point they gave us? 2, 0, 1. It's this one, 2, 0, 1. So we pull that out down here. 2, 0, 1. And then this is equal to 0. So let's do the interior first. 3, negative 1, 4, dotted with this vector x minus 2, y minus 0, z minus 1 equals 0. And now when you do the dot product, you get 3 times x minus 2 minus 1 times y plus 4 times z minus 1. When you do this out, see if I can't make a mistake, 3x minus y plus 4z minus 6 minus 4 equals 0. This is negative 10, so this is 3x minus y, plus 4z equals 10. And there we have it. There's our answer. All right, now you can leave the 10 on the left or you can pull it over to the right. It doesn't matter to me. I think WebAssign wants it on the right. All right, so now let's look at the other problem. All right, so the plane passing through these points. This is a very good problem. 0, 1, 1, 1, 0, 1, and 1, 1, 0. Let me just draw it to the right over here. So we have a point A is 0, 1, 1. Let's have a point B, which is 1, 0, 1. And you have a point C, which is 1, 1, 0. All right, so here we go. So you have to find the plane through these points. Now, I don't know where these points are. I know how to draw these points in space, but I don't really care where they are. Let's just draw a diagram of it. These points are on a plane, okay? So let's call it, suppose this is A, this is B, and this is C. Now, if I do the cross product of AC with AB, so AC cross AB, these are vectors. So there's a vector AC here, vector AB here. If I do the cross product, this will give me a vector N that I need, okay? So here's N, and N will be perpendicular to both of those. We use the right-hand rule, crossing AC with AB. You have your fingers here, fingers on AC, and your palm on AB, fingers and palm. And when you cross on your right hand, your fingers to your palm, your thumb points in the direction of N. So it's in the proper direction. Technically, it doesn't matter which way you cross them. If N goes below, you'll still get the same answer. Don't make a habit of doing that, though, because sometimes it does matter with different types of problems. All right, so let's find AC. Okay, so AC is, let's see, it's going to be 1. I'm subtracting the x's, subtracting the y's, and subtracting the z's. So I get AC, this is AC. This is 1, 0, negative 1. And then AB, let's see, subtracting the x, y, and z. So AB will give me 1 minus 0, 0 minus 1, and 1 minus 1. And this gives me 1, negative 1, 0, like this. And now when I do the cross product of these, I'm going to cross out the first column and then do the cross product of these. So that will be 0 minus 1. And then I cross out the second column and I do the cross product of what's left over, but I go backwards. So it'll be negative 1 times 1, negative 1 times 1 minus 1 times 0, which is 0. Okay, and now I do the I cross out the last one, and I do the cross product of those in the proper order. So it's 1 times -1 is -1, and then minus 0. Shoot. Minus 0. Let me make sure I did the first one right. Cross out the first one, and I get 0 minus 1. Yeah, that's right. Okay. So we get the vector n. So n is -1, -1, -1. And now we use that along with one of the points. So one of the points, I'll just use A, 0, 0, 1, 0, 1, 1. So let's use the point A, 0, 1, 1. This is going to be our R naught. So we have, all right, so n dotted with R minus R naught equals 0 gives, I'm going to pull the negative out of the end. So -1, 1, 1 dotted with x, y, z minus R naught. Here we go, 0, 1, 1. And then that equals 0. And now the negative I can cancel out because I'm going to multiply through by a negative on both sides. So 0 times -1 is 0. So I get 1, 1, 1 dotted with x minus 0, y minus 1, z minus 1 equals 0. And so when I multiply that through, I get 1 times x is x plus 1 times y minus 1 is 1 minus 1. 1 times z minus 1 is z minus 1. This is equal to 0. Not a comma, this is a plus. Dot product is a sum. So I get x plus y plus z minus 2 equals 0. And so it's x plus y plus z equals 2. Now, that's the answer. What I can do is I can go back up. Any point on the plane has to satisfy that equation. So I'm going to go back up and I'm going to pull a random point, one of the 3 other points, the 2 other points. We used A already. I don't want to use that. I want to use C. 1, 1, 0 should work in this. So plug in 1, 1, 0. So we get 1 plus 1 plus 0 equals 2. 2 equals 2. It checks out. And there you go. So that's your plane. Love this problem. It's great. You should know how to do this on the test. All right, that's lines and planes. Good luck on the homework.